Okay, guys, day 4, we're going to do limits to infinity. So far we have done limits where we wound up getting, limits to a number where we wound up getting 0 over 0, and we had a hole in the graph, and you tried to somehow simplify, factor, rationalize, and then replace in the number. Then we also had where we replaced in, and we had c over 0, and there was a vertical asymptote, and we had to approach from both sides, a little to the left, a little to the right, and see if we wind up getting both positive, which means it goes to infinity, or both negative, goes to a negative infinity, or we got a positive and a negative, and therefore the limit did not exist. Okay, today what we're going to do is limits to infinity with 2 different cases. But first, I just want to review this real fast because this is going to come up later in the lesson, and we did this on the review topics day. So remember this, I asked you to write f of x equals absolute value of x as a piecewise function, and we broke it apart to be x where the domain of x is greater than or equal to 0, and negative x where the domain is x is less than 0. And that was the case because here's our absolute value, and we can see that this piece is y equals x, and the domain is x is greater than or equal to 0 because that's this way. And then we did y equals negative x, and the domain is x is greater than 0 because we're going this way. And then on that day also, I showed you that the square root of x squared is also equal to the absolute value of x. So therefore, the square root of x squared can also be written as that piecewise function. Now this is going to come in super duper handy today, that we're going to use this and this together. Okay, so that'll come in later, and that's just for a little bit of the lesson. Okay, so let's do limits to infinity. So let's think logically about this. What are polynomial functions again? Polynomial functions are parabolas, cubic functions. Polynomial functions could be ones that are raised to the 4th power, things like that. So we're going to use the end behavior rules to find limits to infinity. When I ask to find a limit to the infinity, it means I want to go all the way out here to the end, and I want to know what is the graph doing. Or maybe I want to go all the way out here to the end of the graph and see what is that graph doing. So that's why the end behavior rules help us. So let's just review those real fast. Remember, if the highest exponent was even and it was positive, then both ends would be going up. Even negative, remember both were down. Odd positive is righties up. Odd negative was lefties up. So very simply, when I want you to find the limit to infinity of a polynomial function, we're just going to use the end behavior rules. So I feel like you're going to be very good at this. All right, so first one. I notice that this is even negative. So even negative both ends are going to be down. Now, if I'm heading towards infinity, isn't that this way? So if I'm heading this way, I'm going to look at this piece. So the graph is heading towards negative infinity. And that's my answer. Think about it logically as well. If we were to graph this, negative 3x squared, it would look something like this. So if I want to find the limit as x heads towards infinity, that means I'm going this way. So as I go that way, where's the graph going? Where's y headed towards? And y is headed towards negative infinity. Alrighty, so we won't graph it for every single one, but we'll just talk about it. Okay, so now we got odd, and this is positive. So odd positive is righties up. I'm heading towards infinity, so that means this way. So I'll look at this piece. So the limit as we head towards infinity is infinity. Where's y going? That's all they want to know. What is y approaching? I have odd negative. So odd negative is lefties up. And if I'm heading towards negative infinity, that means I'm going this way. So I look at this piece. So positive infinity. Okay, so it's as simple as that for limits to infinity of polynomial functions. You just use end behavior rules. Very, very straightforward. Okay, where we have to think a little bit more is when we do limits to infinity for rational functions. So again, remember what rational functions are. They're that whole unit that we did. Here's a big example of a rational function, fractions, and we got a whole bunch of stuff going on. So we have to use our horizontal asymptote rules when we want to find the limits to infinity on rational functions. Because remember, these guys are big bad boys. They've got vertical asymptotes, maybe horizontal asymptotes, maybe slant asymptotes, holes, all kinds of crazy stuff is happening. So the first two situations, though, are easy. It's just the third situation we have to do, just think about it, do a little bit more work. So we're going to compare, just like we did for horizontal asymptote, we're going to compare the highest degree in the numerator with the highest degree in the denominator. If n is less than d, then the horizontal asymptote is y equals 0, and therefore the limit would be 0, because all the way out at the ends, remember, it's being magnetized towards that horizontal asymptote. If n equals d, remember the horizontal asymptote is the quotient of the lead coefficients. So therefore the limit would be the quotient of the lead coefficients. So these two scenarios are straightforward. What happens when n is greater than d? So we have a lot of steps here, as you can see. So when n is greater than d, remember there's no horizontal asymptote. Now the answer is either going to be plus or minus infinity. So we're going to have to figure that out. It's going to be either one of them. And here's how we do it. So you divide the lead. I'm going to use this example right to the right. Let me just make a little bit more space. Okay. All right, so, sorry, I got distracted. I live pretty close to the hospital, so I heard a whole bunch of sirens. All right, so dividing the lead coefficients. So first thing we're going to do is come on over here, and we're going to divide the leading coefficients. So if I divide them and simplify it, I get 3/2 x cubed. Now use your end behavior rules, which we just did before, and we can see that this is odd positive. Odd positive is going to be righties up. And then if I want to find, and now I'm going to move this up again. I did two scenarios for you. So I did the first one, if I want to know the limit as x goes to negative infinity, just like we did before. I'm heading this way, so use this piece. If I want the limit as x goes to positive infinity, go this way, use this piece. Alrighty, so that's what we're going to do now in this section. We're just going to first identify how can we compare n and d. All right, first round of our rational function, and it's going to infinity. So what do we need to do for all of these questions, 4, 5, 6, and 7? We need to compare n and d. So in the first one, I notice that n is equal to d. If n is equal to d, then it's going to be equal to the ratio. So the horizontal asymptote here would be y equals 1/2. So that's what the limit is, because at the ends, the graph is going to be magnetized towards that horizontal asymptote, just like we did the whole graphing unit on this. Okay, next one. Let's compare. In the next one, I see that n is less than d. If n is less than d, then the horizontal asymptote is y equals 0, so the limit is y equals 0. All right, next, be careful when you compare. Right? You got to find the highest power, so it's to the right over there. All right, so what do we have happening here? Now we have n is greater than d. If n is greater than d, you got to take this off out to the side. You need to simplify it. And now use your end behavior rules. So this is odd, negative. Odd, negative is lefties up. And now we want to go where? Towards positive infinity. So if x is heading towards positive infinity, I'll use this part. So the limit is negative infinity. You can always graph these two and peek and see what they look like to try and understand what's happening here. And you can see that it is correct. Okay, one more. What do we have happening on this one? Oh, I'm using the same example. Same example from here. Okay, so we're just going towards negative infinity now. So negative infinity means go this way, so it would be positive infinity. Alrighty, that's really the whole big part of this lesson that I need you to understand, 4, 5, 6, and 7. So just be great at those. That really would make me happy, 4, 5, 6, and 7, and then just the beginning part that we did, you know, the 1, 2, and 3 in the very, very beginning section, you know, those are good too. Now, you know, this next part's a little hard. I'm just going to show you. I'm not going to put this part on the test, but, you know, it is something I'm supposed to teach you, so let me just show you. And this should not be there. Okay, so it says when evaluating the limit with a radical. All right, so see how this is still a rational function, but now we have a radical in there. So we're going to have to use this from the beginning of today's lesson and back from the review topics. So again, the square root of x squared is equal to the absolute value of x. So watch, which this, remember, can also be written as x and negative x, where x is greater than or equal to 0 and x is less than 0. Okay, so let's come on over here. So I still want to compare, but when I compare, I have to just look at this piece, and I have to decide what component of this am I looking at. So if I'm headed towards positive infinity means I'm going to use this part of the graph. And what is the equation of that graph? It's x. So essentially what I'm doing is I'm changing that blue circle right there to an x. And then I compare that to, I put that over 3x, and now compare. And I can see that n equals d, so it's equal to the ratio. It's not hard. Watch me do the next one. It's because it is very simple. Watch. So now if I want to do this again. So this is either going to be positive x or negative x. That's what I'm going to write on the top of the fraction here. I'm going towards negative infinity. So if I'm going towards negative infinity, which is this way, I'm going to use this piece of the graph, which is this guy. So this becomes a negative x over the bottom, 3x. Remember, we're just comparing again. And here I wind up with the same thing again, so n equals d. So when they're equal to each other, it's equal to the ratio. So I'm going to say this again because it really, truly as simple as that. So when you have the square root of x squared, it's either going to become an x or a negative x. How do you know which one? Well, if you're headed towards positive infinity, it's going to be x. If you're headed towards negative infinity, it's going to be negative x, because it's really just which piece of this piecewise function are you using. Infinity is going to the right. Negative infinity is going to the left. Okay, so let's just try one more. And that's, let's just try one more. Okay. All right, so now I have a 3x squared there. Everybody see that? 3x squared. Okay, so where am I headed? I'm headed towards infinity. So therefore, it's going to be a positive x on top. But you do need to keep that rad 3. Okay, that part needs to stay, because that is still part of the lead coefficient. And then over x. And now compare again. N equals d. So it's equal to the ratio. So the ratio is going to be what? So remember, it's the ratio of what's in front of the x's. So technically, that's just rad 3. Right, because the x's are gone. Okay. All right, so that's good, guys, for this. Homework is, I have it all written down for you there on that to-do list, but I believe it's page 26 and 27, and there might have been something that you didn't have to do, but just look at the list. I think I might have crossed out like 2. Okay? All right, good luck, and really, do the best you can on this, and I do suggest that you watch the videos again, pause it. It's a very short video. All right, we're getting through limits. At least the next unit after this one is definitely easier. I think this is probably the hardest one. All right, miss you guys. Bye.